Let's talk about how you can represent functions using linear models. While the term linear may sound a bit basic, it turns out we can use linear models to represent a wide range of functions. The reason we often use linear models to represent functions is that we can take advantage of a range of tools from linear algebra. For example, we can use linear regression to solve for a function's coefficients given input and output data. But what exactly is a linear model? A linear model is one where the output is a linear combination of the input parameters. Or in other words, we can express the output as a weighted sum of the inputs. If we have m inputs, we can multiply each element of the input by its corresponding weight to get the output. While the output could be multidimensional, we will focus on the simple case where the output of the linear model is a scalar. The combination of the weights and the choice of inputs are the two pieces that define the linear model. Looking at a few examples, first we have a classic example of a line in slope-intercept form. For this model, we can see if the input is the value of x, and the weights are the 3 and 4 corresponding to the slope and intercept respectively. In the second example, we have 3 inputs, denoted by x1, x2, and x3. In this model, the weights are 2, 5, and 6. For any linear model, if we have a set of inputs and the model weights, we can calculate the resulting output. Rather than just calculating a single output, we may also want to calculate the output for multiple sets of inputs. We can do this by concatenating several inputs and outputs into a matrix vector notation for the linear model. Now, instead of having a single set of inputs, we have a matrix of inputs where each row represents one set of inputs. Instead of a single output, we now have a vector y of outputs, where each entry corresponds to the output for a given set of inputs. Finally, we have a vector w for the model weights. In this definition, we have n sets of inputs and n outputs. Each input consists of m entries. There are m weights, which are the coefficients for each of the entries in the input. We can also dig deeper to look at how these vectors and matrices are structured. As we just mentioned, in matrix vector notation, we can represent the relationship for multiple input-output pairs of data. So rather than the single input-output relationship we discussed earlier, you can think that we now have an equation for each set of inputs. Here we add a second subscript to denote which set we are referring to. For example, x subscript 1, 2 means the first element of the input for the second set of data. Notice that we use the same weights for each pair of input-outputs. When we construct our input matrix X, we will put each set of inputs in its own row. So the first row will be all of the entries for the first set of inputs. We repeat this process for the n sets of input. The weight vector will be the weights corresponding to each one of the inputs. Finally, each entry of the output will simply be the output for a particular set of inputs. This notation can be a bit confusing the first few times you use it. To understand how we can use this to model a linear function and calculate outputs, let's look at a few examples. The first example is to develop the linear model for a line in slope-intercept form. The function is y equals 5x plus 2, and once we have the linear model, we want to use it to calculate the output for 4 different inputs. The 4 inputs are when x equals 0, 1, 2, and 3. First, we will write the matrix vector notation to remind ourselves of the format. Next, we will construct the weights vector. The coefficients of our linear model are 5 and -2, corresponding to the slope and y-intercept of the line, respectively. Next, we need to construct our input matrix. As a reminder, we will need a row for each set of inputs, thus we will need 4 rows. The number of columns must match the number of weights, thus we will have 2 columns. Therefore, our input matrix is going to be 4 by 2. Each row will hold 1 set of inputs. The big question is what values go in each row. The first input will be the value of x. The second input corresponds to the y-intercept, which is constant, and thus we will make our second input equal to 1 for each row. In other words, this input doesn't depend on the value of x. So if we put it in all 4 rows, we can see our final input matrix. Finally, we can substitute in our 4 inputs. Now that we've determined our input matrix and weight vector, we can plug them into our formula to solve for the corresponding outputs. We can do this by performing matrix multiplication. After matrix multiplication, we see that our 4 inputs have led to an output matrix with 4 corresponding outputs. The second example is to develop a linear model for a cubic function. The function is y equals 2x cubed plus 4x plus 1. Once we have the linear model, we want to use it to calculate the output for 3 different inputs. The 3 inputs are when x equals 0, 1, and 2. Again, we will start by writing the matrix vector notation. Next, we will construct the weights vector. The coefficients of our linear model are 2, 4, and 1. Next, we need to construct our input matrix. As a reminder, we will need a row for each set of inputs, thus we need 3 rows. The number of columns must match the number of weights, thus we will have 3 columns. Therefore, our input matrix is going to be 3 by 3. Each row will hold 1 set of inputs. Again, the big question is what should these inputs be, and also how can we use a linear model for x cubed? The trick is that the first entry of our input will actually be the nonlinear term x cubed. While our output has to be a linear combination of our inputs, there's nothing stopping us from setting our inputs to nonlinear quantities that we can calculate. The second input will be the value of x. The final input will again correspond to the function constant and be set to 1 for each row. So if we put in all 4 rows, we can see our final input matrix. Finally, we can substitute in our 4 inputs. As an example of this substitution, we'll focus on the bottom row. Our value of x is 2, so the first element of our input will be 2 cubed, which is 8. The second element is just x, so it'll be 2. And the final element is the value for the constant, which is set to 1 for each row. Now that we've determined our input matrix and weight vector, we can plug them into our formula to solve for the corresponding outputs. Again, we can do this by performing the matrix multiplication. After the matrix multiplication, we see that our 3 inputs have led to an output matrix with 3 corresponding outputs. So summarizing this brief lesson, we showed how we can use linear models to represent a variety of functions, including functions that didn't seem like they could have been linear to start with. We also showed how we can use matrix vector notation to solve a linear model for multiple outputs given a set of inputs. It also turns out that in using this matrix vector notation, we've actually set the groundwork for our next lesson, which will focus on how to do linear regression. In the next lesson, we will show that we can use the matrix vector notation to solve for the best fit linear model weights, given a set of inputs and output data.